you probably learned that the speed of light is just a number. 299,792,458 meters per second. Incredibly fast. Faster than anything else we've ever observed. End of story, right? But pause for a moment. Why is it the limit? Why can't anything move faster? What is actually stopping you? Most people never really question this. They simply accept the statement. Einstein said the speed of light is the ultimate speed. Case closed. But repeating a rule isn't the same as understanding it. When you seriously ask why nothing can outrun light, when you push past the memorized explanation, you run into something deeply strange, something that doesn't behave like anything in ordinary life, something that forces you to rethink what space and time even are. Because the speed of light isn't just another speed. It isn't merely the fastest signal in the universe. It's part of the architecture of reality itself. It's stitched into space and time so tightly that moving faster than it doesn't just seem difficult. It becomes physically meaningless. To see why, we need to start somewhere simple, something familiar, something everyone understands. Objects fall. Drop anything, a stone, a ball, whatever you like, and it accelerates toward the ground. In the first second, it falls about 16 feet. That's what Galileo carefully measured centuries ago. Now think about something much bigger. The moon. The moon circles the Earth instead of crashing into it. It stays up there, gliding through space in a smooth orbit. So it looks like it isn't falling. But look closer. Is the moon actually falling the entire time? Imagine freezing the moon in place, no sideways motion at all. What would happen? Gravity would immediately pull it straight toward Earth. It would drop, just like the stone in your hand. But the moon is moving. It's racing sideways along the curve of its orbit, and while gravity keeps pulling it inward, that sideways motion makes it continually miss the Earth. So the moon is falling, but it's falling around the Earth instead of into it. The moon is constantly dropping toward Earth, yet it never hits. That's what an orbit really is. Endless falling combined with just enough sideways motion to keep missing the ground. And this is where Newton's insight changed everything. He noticed something simple but powerful. The moon is about 240,000 miles from Earth's center. We, standing on the surface, are only about 4,000 miles from that same center. So the moon is roughly 60 times farther away than we are. Newton asked a bold question. What if gravity becomes weaker with distance? Not just a little weaker, but following a precise mathematical rule, an inverse square law. That means go twice as far gives gravity becomes 4 times weaker. Go 3 times as far gives it becomes 9 times weaker. In general gives the strength drops with the square of the distance. If that rule is true, then at the moon's distance, 60 times farther away, gravity should be 60 squared times weaker. That's 3,600 times weaker than gravity here on Earth. Now think back to Galileo's measurement. Near Earth's surface, falling objects drop 16 feet in the first second. If gravity at the moon is 3,600 times weaker, then the moon should fall toward Earth by 16 feet divided by 3,600. Do the calculation, and you get roughly 1/12 of an inch per second squared. That sounds tiny, almost nothing. But here's the astonishing part. Because falling distance depends on time squared, that tiny 1/12 of an inch, when scaled correctly, builds up to the same 16 feet we measure on Earth. And when Newton computed how far the moon should drop toward Earth in a single second, assuming the inverse square law was true, the numbers matched reality perfectly, exactly the rate required for the moon's orbit. This was enormous. Not just an idea, not just philosophy, a testable prediction that worked. Newton connected two completely separate facts: how objects fall here on Earth, how the moon moves in the sky. One law, explaining both. For the first time, the heavens and the Earth were no longer separate worlds. They followed the same rules. And that realization would eventually lead us step by step to Einstein and to the mystery of why nothing can move faster than light, to things that once seemed completely unrelated suddenly became expressions of a single rule, the law of gravity. After that, there was no turning back. But Newton didn't stop there. He pushed the idea further. If gravity truly follows an inverse square law, then the paths of planets shouldn't be random. Their motion should have a precise mathematical shape. So Newton worked it out, and the answer he found was unexpected yet beautiful. Planetary orbits must be ellipses, and when astronomers looked at the sky, that's exactly what they saw. Years earlier, Kepler had carefully measured that planets move in ellipses, but he had no explanation for why. Newton provided the reason. One law of gravity suddenly explained. Falling apples, the moon's orbit, and the motion of planets. 3 mysteries, resolved by a single idea, and the deeper scientists looked, the more pieces began to fall into place. Take the tides. Why does the ocean rise and fall each day? Because the moon pulls on the Earth. That seems simple enough, but there's a problem. If the moon's gravity only pulled the oceans toward it, you'd expect one high tide each day, a single bulge of water on the side facing the moon. But that's not what happens. Instead, Earth experiences high tides, roughly every 12 hours. So, what's really going on? For a long time, people argued. Some thought the Earth was being pulled away from the water. Others believed the water itself was being pulled toward the moon. Each idea captured part of the truth, but neither told the whole story. Newton saw the deeper pattern. The moon's gravity doesn't pull equally on every part of Earth. The side closer to the moon feels a slightly stronger pull. The center feels a bit less, and the far side feels weaker still. It's this tiny difference in force, this stretching effect across the entire planet, that creates two ocean bulges, not one facing the moon, and one on the opposite side. Once again, a hidden pattern revealed itself, and once again, gravity explained something that had puzzled people for centuries. But even Newton's masterpiece, as powerful as it was only part of the story, because gravity, space, time, and the ultimate speed limit of the universe were still waiting for a deeper explanation. The key detail is subtle but crucial. The ocean on the side of Earth closest to the moon is slightly nearer to the moon than Earth's center is. So the moon's gravity pulls that water a little more strongly. On the opposite side, the ocean is farther from the moon than Earth's center. So that water feels a slightly weaker pull. Those tiny differences stretch the oceans into two bulges. One where water is pulled toward the moon, another where water is effectively left behind, because Earth itself is pulled a bit more strongly than that distant water, and that's why we experience high tides each day. But there's another layer to the story. Earth and the moon aren't in a simple one-sided relationship, where the moon circles a stationary Earth. Instead, both bodies orbit a shared center of mass, a point located slightly inside Earth itself. So, in a sense, Earth performs the same graceful motion as the moon. Both are moving in a slow circle around an invisible balance point. From this perspective, the tides can also be understood through motion. Some ocean water is flung outward a little more than the solid Earth, while other water is drawn inward a little more strongly. Different viewpoints, same physical reality. And once this picture became clear, many other mysteries suddenly made sense. Why is Earth round? Because gravity pulls everything toward the center. Why isn't it a perfect sphere? Because Earth is spinning, and that rotation pushes the equator outward slightly until gravity and motion balance. Why are the sun and moon round as well? For exactly the same reason. Gravity shaping matter into the most stable form possible. As measurements grew more precise, and science advanced century by century, Newton's law of gravity faced increasingly demanding tests. And again, it worked. With stunning accuracy, yet hidden within those precise successes, was a quiet hint, a suggestion that Newton's picture, as powerful as it was, might not be the final description of reality, and that hint would eventually lead to an even deeper revolution, one involving space, time, and the ultimate speed limit of the universe. One of the earliest truly precise tests of Newton's laws didn't happen on Earth at all. It happened far away, among the moons of Jupiter. Astronomers watched those moons carefully, tracking their orbits over long stretches of time. If Newton's law of gravity was perfectly correct, Their motion should match the calculations exactly, but something strange appeared. Sometimes the moons seemed to arrive about 8 minutes early, other times about 8 minutes late, compared to where Newton's equations said they should be. 8 minutes is not a tiny error. For celestial mechanics, it's enormous. At first glance, it looked like Newton's law might be failing, but then someone noticed a pattern. The moons appeared ahead of schedule when Jupiter was closer to Earth, and behind schedule when Jupiter was farther away. That's a very peculiar clue. The Danish astronomer Ole Rømer trusted Newton's gravity, so instead of abandoning the law, he asked a different question. What if the problem isn't gravity, but light itself? What if light doesn't travel instantly? What if it takes time to cross the vast distance from Jupiter to Earth? That would mean when we look at Jupiter's moons, we're not seeing them as they are right now. We're seeing them as they were in the past, delayed by the travel time of light. And that idea explains the mystery perfectly. When Jupiter is closer to Earth, light has a shorter distance to travel, so we see the moons sooner. When Jupiter is farther away, light needs more time to arrive, so everything appears delayed. The moons weren't breaking Newton's laws at all. Instead, they revealed something even more profound. Light has a finite speed, and that discovery, quietly hidden inside tiny timing errors in the motion of distant moons, would eventually lead us to one of the deepest truths in physics, that this speed of light is not just fast, it is fundamental to the structure of reality itself. To make sense of the timing shifts, Rømer had to correct the observations for the changing travel time of light, and by measuring how much earlier or how much later the moons appeared, depending on Earth's distance from Jupiter, he was able to calculate something extraordinary: the speed of light itself. This became the first clear proof that light does not move instantaneously. It travels, and it takes time. Pause for a moment and consider how remarkable that is. We didn't discover the speed of light by directly timing a beam of light in a laboratory. Instead, we found it indirectly by trusting the law of gravitation. When observations didn't match expectations, Rømer didn't immediately discard Newton's law. He asked a deeper question: what if the missing piece isn't gravity, but the time light needs to travel? And that question led straight to the correct answer. This moment illustrates something profound about science. When a law truly captures reality, it becomes more than an explanation. It becomes a tool for discovering new laws. Confidence in one truth can reveal another hidden behind it. Without Newton's gravity, astronomers wouldn't have known what Jupiter's moons were supposed to do. And without that expectation, the finite speed of light might have remained unknown for much longer. From discoveries like this, science began to accelerate, each breakthrough unlocking the next, an avalanche of understanding, gathering momentum for centuries, still rushing forward today. But here's where the story turns strange. Because once the speed of light was finally measured, physicists began to notice something deeply unsettling. No matter how carefully they looked, no matter how they tried to test it, light always moved at the same speed. Always the same. No exceptions, no matter who measures it, no matter how fast they're moving. Let's make this tangible. Imagine you're standing still. You switch on a flashlight and measure the speed of the beam. You get the familiar number: 299,792,458 meters per second. Nothing surprising there. Now suppose you climb aboard a train. Not an ordinary train, but one racing through space. At half the speed of light, you point the flashlight forward. In the same direction the train is moving. Common sense tells you what should happen. If motion works the way it does in everyday life, the light should move faster than before. Its speed added to the speed of the train. After all, if you throw a ball forward from a moving train, the ball travels faster relative to the ground than if you threw it while standing still. So you measure the light again, and the result is shocking. It's still 299,792,458 meters per second. Exactly the same. Maybe the measurement was wrong. So you try again, this time pushing the train to 90% of the speed of light. You shine the flashlight forward. You measure carefully. Same number. Now you're determined. You push the train to an absurd extreme. 99.9999% of light speed. You repeat the experiment one more time. And once again. The speed doesn't change. Light's speed never adds to your motion. It never combines with the speed of the source. It remains perfectly constant, no matter how fast you chase it. This should feel deeply unsettling, because it violates everything your everyday experience teaches you about motion. In ordinary life, speeds add. Walk forward inside a train moving 50 miles per hour, at just 3 miles per hour. And to someone standing outside, you're moving 53 miles per hour. Simple, logical, familiar. But light refuses to obey that rule. No matter how fast you move, light always races away from you, at the same unchanging speed. So, what could possibly explain this? Einstein realized something extraordinary. The problem isn't with light. The problem is with our assumptions about space and time themselves. And this idea is so strange, so completely opposed to everyday intuition, that even more than a century later, many people still struggle to truly accept it, because Einstein's insight changes something fundamental. Time and space are not rigid. They are not an unchanging stage on which the universe simply acts. They are flexible. They can stretch. They can compress. They can bend, all to preserve one rule. The speed of light must remain the same. When you begin to move faster and faster, time itself responds. Your clock doesn't just appear to slow down. It actually ticks more slowly. At the same moment, distances in the direction of your motion don't merely look shorter. Space itself becomes contracted. These are not illusions, not tricks of measurement, not mistakes in observation. They are real physical changes in how time flows and how space is measured, and the universe adjusts them by exactly the right amount, so that every observer, no matter how fast they are moving, still measures the same speed of light. Think about that. The cosmos continuously reshapes time and distance themselves, just to protect this single constant, which means the speed of light is not merely a fast speed, it is a structural feature of reality, a deep rule woven into the fabric of space and time. Space and time are built so that this speed is identical for everyone. And now the story turns stranger still, because if you try to push anything, a particle, a spacecraft, anything at all, closer and closer to the speed of light, something remarkable happens. The nearer you get, the more difficult it becomes to go any faster. It's not that you simply run out of fuel. It's not that your engines become too weak. Something deeper happens. The object itself begins to resist acceleration more and more strongly as its speed increases. In relativity, this effect is often described as an increase in relativistic inertia. The faster you move, the harder it becomes to push you faster still. And as your speed creeps closer and closer to the speed of light, that resistance doesn't just grow a little. It grows without limit. To actually reach light speed, you would need infinite energy. And infinite energy is impossible. So anything with mass, a person, a spacecraft, even a single atom, can approach the speed of light, but can never reach it. Not because of bad engineering, not because of missing technology, but because the geometry of spacetime itself forbids it. Light is different. Photons carry no mass at all, zero, and massless particles don't merely happen to move at light speed. They are required to. They have no rest state, no slower option. They always move at that cosmic speed. Matter, on the other hand, can only get arbitrarily close, 99.9999% of light speed, closer and closer forever, yet never quite arriving. It's as if the universe itself says, this far and no farther, which naturally leads to a deeper question. Why? Why is reality arranged this way? Why should there be a universal speed limit at all? And here comes the frustrating truth. There isn't a deeper mechanical reason hiding underneath. The speed of light isn't a rule placed on top of the universe. It is a consequence of how the universe is built from the ground up. because space and time are not truly separate things. Space and time are not separate ingredients of reality. They are woven together into a single fabric, space-time. And space-time isn't just an empty stage. It has a geometry, a deep internal structure that determines how events can unfold. Built into that structure is a fundamental conversion between distance in space and duration in time. That conversion factor is what we call the speed of light. So it's not that light itself is uniquely special. What's truly fundamental is that space-time allows only a maximum rate at which cause and effect can travel. Light simply moves at that limit because light has no mass, but the limit would exist even if light did not. The speed is a property of space-time itself, not of any particular object within it. Here's another way to picture this. In everyday thinking, space and time feel independent. You move through space, while time quietly flows forward to separate things. But relativity tells a different story. You are always moving through space-time at a constant overall rate. Always. What changes is how that motion is divided between space and time. If you're sitting completely still in space, then all of your motion is directed through time. You advance into the future at the maximum possible rate, 1 second per second. But the moment you begin moving through space, some of that motion must be redirected. Now you're traveling partly through space and partly through time, which means your progress through time slows down. The faster you move through space, the slower you move through time, and there is a final boundary to this trade-off, a maximum possible speed. If something could move through space at exactly the speed of light, there would be no motion left for traveling through time. Time, for that traveler, would simply stop. This is why light itself does not experience the passage of time from the viewpoint of a photon. The moment it is emitted and the moment it is absorbed are the same instant. No waiting, no duration, no ticking clock, a frozen universe. And this reveals the true barrier. You cannot go faster than light because you cannot have less than zero motion through time. That boundary, that absolute edge, is the real speed limit of reality. And here is the most beautiful part of all. This is not just elegant theory. It has been tested again and again in the real world. In particle accelerators, tiny particles are pushed to 99.9999% of light speed, exactly as relativity predicts. Each extra bit of speed requires dramatically more energy, closer and closer to light speed, yet never reaching it. High above Earth, GPS satellites orbit at great speed and sit in weaker gravity than we experience on the ground. Because of this, time flows differently for them. If engineers ignored relativity, GPS positions would drift by miles within a single day. Modern navigation works only because Einstein was right. Even cosmic rays quietly confirm the same truth. They create unstable particles, muons, high in the atmosphere. By ordinary expectations, those muons should decay long before reaching Earth's surface. Their lifetimes are simply too short, but they are traveling extremely close to light speed. For them, time runs more slowly. From their own perspective, they survive long enough to reach the ground. From our perspective, their lifetimes appear stretched because of their motion. Either way you describe it, the result is the same. More muons arrive than classical physics allows, exactly as relativity predicts. This isn't guesswork. It isn't philosophical speculation. It is measured reality. This isn't speculation. It's measurement. The idea that the speed of light is a true limit has been tested as rigorously as anything in all of physics. So let's gather everything we've uncovered. Why is the speed of light the ultimate limit? Because spacetime itself is built with a maximum rate at which cause can lead to effect. That rate is what we call the speed of light. Not because light is magical, but because spacetime contains a fundamental conversion between distance and duration, between space and time. To go faster than this limit would mean pushing beyond the structure of spacetime itself. It would require effects to appear before their causes. It would mean moving backward in time and doing the very order that makes reality coherent, and that simply cannot happen. So the speed of light becomes something deeper than motion through space. It is the speed at which information can travel, the speed at which forces can influence, the speed at which the present moment now spreads across the universe, the ultimate rate of change, the boundary of possibility, and the path to this understanding didn't arrive all at once. It began when Newton watched the moon and uncovered gravity. Then Rømer studied Jupiter's moons and revealed that light has a speed. Then Einstein realized that this speed is constant for everyone, and from that single insight, rebuilt our understanding of space and time. After that came thousands of experiments, each one confirming, refining, strengthening the picture, discovery building on discovery, insight opening the door to deeper insight, an avalanche of knowledge, rolling forward for centuries, and still accelerating today, because the speed of light isn't just a number written in a textbook, it is a key, the key that unlocks how space and time truly work, the key that reveals a universe far stranger and far more beautiful than common sense ever imagined. And perhaps the most astonishing part of all is that we can understand it, we can measure it, test it, use it to predict the unseen. That is the real beauty of physics, not comfort, not simplicity, truth.